to continue today. So last time I was talking about, basically, I still continue talking about Bus-Sur theory. And last time we were talking about amalgamated products of two groups, and shown that amalgamated product, if the group is an amalgamated product, then it acts on a tree. And actually, and the converse is also true, that if a group acts on a tree and the factor graph, like the graph of orbits for this action, is a segment, then the group is an amalgamated product. And I'll start with an example today. So let's take SL2Z. So special linear group, 2 by 2 matrices with determinant 1. So it acts on the hyperbolic plane, and I will show that it acts on a tree. This is kind of the very nice example of an amalgamated product. So the hyperbolic plane is going to be taken like this model. So we take upper half plane. So imaginary part of numbers is greater than 0, and like a hyperbolic line, then it is an open half circle or an open half line in the Euclidean sense in H2, and the closure should meet the real axis at right angles. So this model. Now the Möbius transformation of hyperbolic plane is this map, like point is taken to AZ plus B divided by CZ plus D, where A, B, C, D are real numbers, and AB minus BC equals to 1. So basically, SL2R acts on the hyperbolic plane by Möbius transformation. So if you have a matrix A, B, C, D, so such that the determinant is 1, so matrix is an SL2R, then this matrix acts on point Z by this Möbius transformation. And the kernel of this action is plus or minus 1. So it's actually PSL2Z acts faithfully this way. Okay, now, just a minute, let me turn off the phone. Okay, so now the fundamental domain for the action of PSL2Z is the following shadowed region. So it's points, absolute value is greater than 1. Then a real part is between minus 1/2 and 1/2. So this is included, like this line is included, and this, like this half line is included. So this is a fundamental domain. So the whole plane can be obtained by transforms like of this area under the action of PSL2Z. Okay, then this arc, like the images of this arc, this Q, point Q, this point P. So this arc is the set of points EI alpha, where alpha is between pi over 3 here and pi over 2. One can show that so the images of this arc under the action of SL2Z is a tree. Like you can see, like we are getting all this arc, like this, and so on. So it is a tree, and SL2Z acts on this tree without inversion. Oops. Without inversion on edges, and distinct points of this arc are not equivalent, so they're in different orbits. Now the stabilizers of the endpoints, one can just, I mean, we know how it acts. It acts by Möbius transformations. So one can compute the stabilizer of point Q, which is this matrix, and the stabilizer of the point P. And then, so this has order 4. A has order 4, B has order 6. And so according to the general theorem, then SL2Z can be, so A generates a cyclic group of order 4, B generates cyclic group of order 6. The intersection of the stabilizer of the H, it is the intersection of the stabilizers of the end vertices. And so we get that SL2Z is isomorphic to the amalgamated product of Z4 and Z6 amalgamated over Z2. Because the stabilizer of the arc, it is the intersection of these two subgroups. It's generated by this matrix and has order 2. So this is a representation of SL2Z, I mean, which certainly was known like before SIR, but like this is a proof that it has this representation as an amalgamated product by proving that it acts on a tree and considering the factor graph. So the factor graph is a segment. Now also we can get the presentation of GL2Z. Like if you consider this matrix, then the previous matrix A and C, they generate dihedral group D4, and B and C generate D6, and we can get GL2Z as amalgamated product of D4 and D6 over D2. Sir also shown in his book that for n greater or equal than 3, SL2Z and GL2Z cannot act on trees. So they do not act on trees, so they're not splittable. They cannot be represented as non-trivial amalgamated products. So it's only for 2 these groups are splittable. So that's this example. Now I was thinking whether I should do it or not, but I would like to say like more about the general theorem of Basser theory. And for this, we also have to, like we sort of covered amalgamated products. Now let's talk about H&N extensions. It's a very similar construction, but if amalgamated product corresponds to a segment graph, then H&N extension corresponds to a loop graph. So suppose we have a situation. So we have a group H, and 2 subgroups, 2 isomorphic subgroups, A and B of H. So let phi be isomorphism between A and B. And then we can construct a group, larger group, where these subgroups actually going to be conjugated. So this isomorphism will become an inner restriction of inner automorphism. So, and this is called Higman-Neumann construction, H&N extension. So G is like we take our group H, we add extra letter T, which is called stable letter, and then we conjugate elements from A by T into their images. Like we just add these relations. For every element in A, we say the T inverse AT is phi of A, which is element in B. And again, like very often, one doesn't have to add all the relations for each element of A, because it's basically, we need to add relations for generators of A only, because then it automatically gives the image of arbitrary element of A. And then this group, like amalgamated products, elements have very nice normal form. And so normal form is again a sequence of like alternating sequence of this T to the power plus or minus 1. And okay, G0 is arbitrary element in H, but G1, Gn are again right coset representatives of, like we can represent H as a union of right cosets of right cosets of A, and H is also a union of right cosets of B. So these elements G are right coset representatives, and moreover, so if epsilon I, for example, if epsilon 1 is -1, then G1 belongs to A right coset representative of A. And if epsilon is, so if it's -1, then Gi is an A. If it is 1, then Gi is a coset representative of B. This is basically like why it is, because we can write arbitrary element as a alternating product of powers of T and elements from H, right? Because these are all the generators, like T and H. So we can always write it like this. So for example, suppose we have something like at the end of the word, so we have something, and then we have like T inverse, okay, T inverse H. And here, like it is H1.
I can only see part of what you write.
You don't see, you don't see what
the bottom. Okay, I see. Okay, now I see it.
Okay, so for example, like this is something, and then it ends on H1 T inverse H. So let's represent H as A G, where G belongs to transversal for A. Like every element in H can be represented as a product of element from A and element of the right transversal of A. So then this can be rewritten as like H1 T inverse AG. But and something here. But what is T inverse A? T inverse A, like if you look at the relation, T inverse A is the same as corresponding element from B, like phi of A times T inverse. So this is like corresponding B times T inverse. And I can, then I'll just put this A goes here and becomes B, right? So I'll have H1B, and then I just joined it with H1, T inverse G. And like then the tail of the word has this form, right? So T inverse epsilon equals -1, and then G belongs to the right transversal for TA. And what is left is becoming shorter, and so we can get it into this normal form. And we can prove, like similar to how we did for amalgamated products, that this normal form is unique. And this, like the existence of a normal form, it's basically like this is that this theorem, the theorem about normal forms, it's one of the key players in the Boole constructions of groups with undecidable word problem, or Novikov construction, and many other like classical constructions in group theory, because existence of normal forms allows to show that some word is not equal to 1. Like if you have a non-trivial normal form of the word and it's not empty, then the word cannot be equal to 1. Like this follows from the uniqueness of normal forms. So these are like a lot of HNN constructions are used by Novikov and by Boole, and in other like classical theorems in 50s. Okay, so that's now uniqueness of normal form. Like for example, this is like Britton's lemma. This is like what I was referring. So every element has a unique representation in the normal form. H is embedded into HNN extension by the this identical map H sent into H. And if this expression does not contain subverse T inverse G, like suppose we have this expression and it is not a normal form. So if it does not contain subverse like this, where GI is in A, or like this, where GI is in B, then this word is not equal to 1 in G. Again, like how Britton's lemma is used in constructions of groups with undecidable word problem, it's like it's kind of, usually there is some interpretation of a Turing machine, like with undecidable halting problem. Now, if the machine stops, then it's like the work of the machine is mimicked by the relations of the group. So then some element is equal to 1. But if the machine does not stop, one has to show that the corresponding like element constructed for the configuration of the machine is not equal to 1. And this is like the key points how to show that something is not equal to 1, because the group is constructed using a lot of H&N extensions, and you can use normal forms. But for us, like for the trees, we have this theorem, which I won't prove, but I'll just mention. So, okay, if the group is an H&N extension, then there exists a tree on which this group acts without inversion on edges, such that the factor graph is a loop. A loop is like this. So it's a loop. Moreover, there is a segment, like, so it is a tree on the top, right? So there is a segment y tilde. So this is my tree X, and this is a factor graph here downstairs. There is a segment y tilde such that the stabilizers of each vertices and edges are equal to, so this is H and this is TH T inverse. So basically, again, like we take a factor graph, so this is going to be my group H. Let the T will correspond to this loop. And so H&N extension acts on a tree. And like this is an example. So suppose like we just take a group, instead of H, we take L, and A and B are the same. So basically this is just says that element T, this new letter T, commutes with subgroup C. Then the tree looks like this. So there is a vertex which corresponds to the tree constructed using again left cosets of so vertices are left cosets of H and of L here, okay, GL in this case, and edges are left cosets of C. So like look, so there is a vertex which corresponds to L itself, right? And then this is a left coset TL. And the stabilizer of L of this vertex is L. Stabilizer of TL is TLT inverse, right? So it stabilizes TL. Now the intersection of these subgroups is C, right? Because C belongs to L, and intersection of the stabilizers, and C also belongs, C is the same as T inverse CT, so it also belongs to the stabilizer. Like stabilizer here, it's TLT inverse, the group which is assigned to this vertex, and so on. So the valency of each vertex, it is the index of what, of C in L, right? You can see that these are like edges correspond to left cosets of C in L, and so on. So there is like this approximately how it's infinite tree. This is approximately how the tree looks like. So if the group is an H&N extension, then then it acts on a tree, which is made of left cosets of the subgroup which we extend. And conversely, I'll skip the proof. And the fact that this is tree follows from the uniqueness of normal forms of elements of H&N extension. And then the converse is also true. So if a group acts without inversion on edges on a tree X, and suppose that the factor graph is a loop, like what, like this, one vertex and one edge, then again, we can take arbitrary segment in this tree, denote its vertices like P and Q and H by E, and then take their stabilizers, and then let X be an arbitrary element which takes P to Q. They are in different orbits. I mean, they're in the same orbit, right? Because the graph of orbits only has one vertex. So in the tree, every vertex, all vertices are in the same orbit. So let X takes P to Q, denote by G prime, conjugate of G of the stabilizer of the H by X. And then the group actually, then we take H&N extension of stabilizer of P by letter T, and over the subgroup over the stabilizer of H, and then this is an isomorphism. So if the group acts on nicely on a tree, and the factor graph, the graph of orbits, is a loop, then the group is an H&N extension. And again, like this H&N extension of the stabilizer of arbitrary vertex by letter T, and the associated subgroup is a stabilizer of the H. Okay, so now we've done amalgamated products and H&N extensions. Again, let's skip this. Now let me give a general definition. So this is a generalization of an amalgamated product. It's a definition of a graph of groups. So graph of groups consists of a graph and groups. Now to each vertex of the graph, we assign a group. A graph should be connected. So it just should be connected graph. We assign a group. To each edge, we also assign. Now edges, we think about edges like two edges in one. So we can make an arrow, then it's going to be E if we read it in the right direction, and E bar, like E bar. And then E bar if we read it in the opposite direction. So, and then, so to each edge we have a group GE. Then, so for each, we have a graph. For each vertex, we assign a group. For each edge, we assign a group. And we have a monomorphism. So basically embedding of like sigma. We have GE into G sigma E. Now, since we consider E bar like the H in the opposite direction, then this means that we also have embedding. So H group is embedded into original vertex and the terminal vertex of the corresponding edge. So like it's, so this is a graph of groups. And then the fundamental graph of, fundamental group of the graph of groups. Maybe let me, I mean, I can do certainly, like I can define relations and generators, but I think that the easier would be like to do the following. So let's just, in any case, we have to select maximal subtree in this graph first. Let's select maximal subtree. Now every graph has a maximal subtree, right? By Zorn's lemma. But here we kind of deal with finite graphs. So this is
sigma sigma of E is the starting vertex of the edge, and tau of
And tau is the terminal vertex, yes.
yes.
Yes, tau is the terminal vertex. So, okay, now we select maximal subtree arbitrarily. And then what we do, we take like, okay, so this is a segment, right? Like this is a segment. We take amalgamated products of the corresponding vertex groups over the corresponding edge group. Then we have like, this is a segment. We take amalgamated product of what we got here with this vertex. Then we take amalgamated product of what we got out of 3 of them with this group of this vertex along the edge. And then like for this vertex, and then like for this vertex. And then we take like GE is embedded. So basically we have a group like a tree product made of amalgamated product for this maximal subtree. And then we take two H&N extensions corresponding to this H, because like this red tree now we can kind of consider the corresponding group. You can consider this as one vertex, and then these two edges is going to be like this, right? So and then we take two H&N extensions corresponding to these edges. This is and what we get, it's called a fundamental group of graph of groups. Now I can now talk about like its relations. So basically what we do, like generators, we take a union. So suppose we have a graph of groups. Gamma is a graph. No, gamma is a collection. Like not gamma, this calligraphic G. It's a collection of groups assigned to vertices and edges. And X is a graph. T be a maximal subtree. Suppose that these groups are given by presentations, like so XV is a set of generators, RV is a set of relations, and we define the fundamental group of the graph of groups by generators and relations. So the generators are going to be union of all these X's and new letter TE for every H. But then also then we say that relations are going to be relations of all these vertex groups. And in addition, we say that TE conjugates sigma of G, like for every H, for every element of the H group, we conjugate sigma of G by letter TE to tau of G, right? And then we say that T of E bar is the same as TE inverse, which is kind of natural. Like if we go along the edge, one direction, we think about TE, in the other direction, we think about TE inverse. And then we also kill all the letters T for edges in the tree. So basically for the edges which belong to this red tree, which like was on the previous slide, like the letter T is killed. So we just say sigma G equals tau G. But these are relations of the amalgamated product. So as a result, we do exactly what we did, like I said here. So we take amalgamated product along the edges of the tree, and then we take H&N extensions, because only letters T for these two edges are not going to be killed. And what is this is called the fundamental group of a graph of groups. Okay, so what I can say that the fundamental group of graph of groups actually does not depend on this on which maximal subtree we select. One can show, like one can construct this group as a group of certain loops. It's actually like, I mean, one can like suppose we fix some vertex. Let me just talk a little bit more about this. Like, and if this is just a graph, like what is the fundamental group of a graph? It is a group generated by, like we have a generator for each loop, right? And there are no relations here because it is a graph. But now we have a graph of groups. we can generate it by the following element. So we go like along the H, we read TE, then we take some element from this group. Then again, we go along the H, we read TE, then some element in this group, and so on. So it's kind of group of loops, but loops with elements of the vertex groups added. So that's exactly the group which is going to be isomorphic to the fundamental group of graph of groups, how I defined it. And it doesn't depend on the tree. And now we can formulate also, if instead of the group, we consider Ehrenberg-MacLane space of the group, then we have a fundamental group of a graph of spaces. Like if I draw a surface, or maybe later. Now some examples. So if the graph is a segment, then the fundamental group of a graph of groups is just an amalgamated product. If the graph is a loop, one vertex in the loop, then we have H&N extension, which we can also denote like this, H&N extension of GV. Now, if the graph is like this, so if the graph is a tree, then the fundamental group is called a tree product. So we basically just take amalgamated products along all these edges. Now, if you have many loops and one vertex, then we talk about the so-called generalized H&N extension. Now, this construction, now here I'm talking about spaces, but something like this. So let's consider some complicated surface, right? Like this, and maybe curves. Like you can think about this, like when I shown these two curves, then what we have? We first take amalgamated product of these two groups, right? And then we take an H&N extension. And you can do with instead of fundamental group of graph of groups, you can consider a graph of spaces, and then it's going to be actually a fundamental group of the space which you construct by similar operations as we discussed last time. So it is a fundamental group of some space. Okay, now the main theorem of Bass-Sor theorem. And then I'll just talk about applications. So in one direction, suppose we have a fundamental group of graph of groups, G. So here we have graph is Y, and T is a maximal subtree. Then there exists a tree on which this group acts without inversion on edges, such that the factor graph by this action, so the graph of orbits, is actually isomorphic to Y. And stabilizers of vertices and edges in X are conjugate to the canonical images in G of the vertex groups and H groups. And one can even say more, but maybe I won't say this for now. So basically, if you have a fundamental group of graph of groups, we can construct a tree on which this graph group acts, and then stabilizers of vertices are going to be conjugates of the vertex groups in this fundamental group of graph of groups. Stabilizers of edges are going to be conjugates of edge groups. And the construction of the tree, it is like this. So vertices, like points of this complex. So it's just a union of left cosets of vertex groups, edges, union of left cosets of edge groups. Now, sigma of left cosets, so sigma of this edge, sigma of GE, it's going to be left cosets of the corresponding vertex group, G of sigma E with the same representatives. But for tau, we have to, so tau of GE, we have to put this letter TE in here. So again, like if it is, if the H does not belong, if the H belongs to the tree, then there is no this letter T, because letter T is 1. If the H does not belong to the tree, then the letter appears here. So in one direction, we have fundamental group of graph of groups. It acts on a tree. In the other direction, suppose the group acts, again, without inversion on a tree. Take a canonical projection, group GX, take a canonical projection, take a maximal subtree in the canonical projection. So we have tree, the group acts on a tree. We take a canonical projection, got some graph. Now we can lift this graph like this. So the tree we can lift. No, the tree is like this, right? So we can lift the tree. And we can lift this H, which is, for example, this, right? And then basically what we're saying that if the group acts on a tree, then we take these points P, Q, R. Then this is stabilizer of P, stabilizer of Q, stabilizer of R. And now this point belongs to the orbit of one of those. Like here on the picture, it belongs to the like this point and this point, they belong to the same orbit. So then this is a conjugate. So we have some letter T corresponding to this H. So it's like it's both ways. If the group acts on a tree, we have this, and if the group is, then it is a fundamental group of some graph of groups, and we know like what are vertex groups, what are edge groups. And if it is a fundamental group of a graph of groups, then it acts on a tree. Okay, now corollaries. Let me just, so going to give a proof, but first of all, like the theorem I began with. So the group is free if and only if it acts freely by automorphisms on a tree. Okay, so if the group is free, it acts on its Cayley graph. And it acts certainly freely on the Cayley graph because stabilizer of each point is trivial. And the Cayley graph of a free group is a tree. Now, suppose the group acts freely on a tree. Why it is a free group? What means freely? Stabilizer of each point is trivial, right? So all GV are going to be trivial groups. There are no stabilizers of points. So vertex groups are trivial. And then, like, what are the relations? So we got some factor graph. But like, what are the relations? The factor graph looks maybe like this. Okay, so GV1, which is trivial, GV2, which is trivial, GV3, which is trivial. Maybe something like this, right? So these groups are trivial. And so what are we left with? We're left with this letters TE for non-tree edges, right? So TE1 and TE2. And no relations for them because the letter conjugates trivial element into trivial element. So basically we got a free group generated by these two letters. So if the group acts freely on a tree, then it is a free group, and generators of this free group actually like this stable letters T, which correspond to non-tree edges of the factor graph.
Excuse me?
Mm-hmm.
How do you know that the factor graph is finite, or does it not matter if it's infinite?
basically it does not matter.
Okay.
It does not matter. Yeah, it's like if the group is free, then I mean, so all the stabilizers of vertices are going to be trivial. So finite or infinite, it's just like maybe there are infinitely many edges, like this H and N edges.
Okay.
Okay,
Thank you.
now then the subgroup, okay, the subgroup theorem. The subgroup theorem basically says that a subgroup of the fundamental group of a graph of groups is the fundamental group of a graph of groups itself, right? Because like we have a group, we have H is a subgroup of G. Now G is a fundamental group of a graph of groups, so G acts on a tree. H is a subgroup of G. So H also acts on a tree. Therefore, by the converse of the theorem of Basser, therefore H is a fundamental group of graph of groups itself. Moreover, we can say that vertex groups of H are conjugates of subgroups of vertex groups of G, right? And H groups of H are conjugates of subgroups of H groups of G. Like, for example, from here, we can get a Courage subgroup theorem, right? So what is a subgroup of free product? Like if we have a free product, it is what? It is free product corresponds to this graph, right? To a tree. So free product is V1, GV2. And these groups, H groups are trivial. So free product is a fundamental group of this graph of groups with trivial H groups. So if you take a subgroup of free product, like what is a factor? Take a subgroup. The subgroup acts on a tree, and then the factor graph, it's maybe like it acts on a tree. The factor graph is larger than, maybe larger than, oops, what did I press? Maybe larger than this graph, right? It can have more vertices because there are more orbits. Like H is a subgroup of G, so G has orbits, but H has more orbits because the group is smaller itself. So it is some graph. Maybe it has loops. But what we can say that all H groups are going to be trivial also, right? Because they are conjugates of H group. So the fundamental group, a subgroup of a free product, it is a free product of conjugates of like this terms, right? And some free group. And this some free group, it comes from this like stable lattice T again, because it might be some cycles in the quotient graph. So like Courage subgroup theorem, it's like particular case of this. And then we can say some other things. Like, for example, if you have a finite subgroup in the fundamental group of a graph of groups, then where it is sitting, it must be sitting in a conjugate of some vertex group, right? Because otherwise, I mean, it is not splittable. Finite subgroup, it is not an amalgamated product. Amalgamated product has like, it will be infinite. Then what else? What are the corollaries? Like we can, yeah, we know like which elements are conjugate or can be equal in the fundamental group. Like fundamental group of graph of groups also has nice normal forms, which are generalization of normal forms of amalgamated product and H&N extensions. So that's about Basser theory. Now have some time, so let me just do some like advance to the next. So next time, what I'm going to talk about? Next time I'm going to talk about R trees, and to see, maybe I'll have time to say a little bit more about lambda trees, because the results we have are about lambda trees. So lambda is an arbitrary ordered abelian group. But R trees, so they are generalization of normal trees. And they are basically zero hyperbolic metric spaces. And they have zero hyperbolic metric spaces. They do have tree-like properties, which like I'll remind next. Also, R trees. Why R trees are good and interesting? Because they occur as limits of action of groups on normal simplicial trees. That's their main source of obtaining R trees. So again, like I'll give definitions next time. Like, but what we often have, like for example, a group acts on a sequence of trees. So there is like infinite sequence of actions. Like as an example, so take a free group, no, not a free group, arbitrary group, and take homomorphisms into a free group from this arbitrary group G. Suppose we have infinitely many different homomorphisms into a free group. So basically, then it acts through these images on the Cayley graph of a free group. It acts on a tree. So we have a sequence of actions of the same group on a tree. And then there is a like Gromov-Hausdorff topology. So often such a sequence of actions converges to the action of this group on an R3, on this like zero hyperbolic metric space. So this is how R3s occur, like in group theory, in topology. They occur like in Thorsten's theory, but like for me, it's really, they occur like from when we, for example, when we take solutions of equations in a free group, then we have a sequence of actions of certain group on trees, and then the limit of the sequence give us an action of the same group on an R3. So this is how R3s occur, and sometimes like other lambda trees occur, and I'll like groups which, so for R3s, one can ask the same question. So suppose group acts freely on an R3. Is it still a free group or it is something else? And it is something else, but it is a very nice description, which is called Tripp's theorem. So this is what I'm going to talk about next time. So I'll talk about description of more about R3s, about how they occur, about description of groups acting freely on R3s, and say a couple of words about lambda trees. Okay, thank you very much. That's all for today.
Thank you very much. Are there any questions or comments?
I have a question.
Go ahead.
Yes?
Yes, go ahead, please.
So I know that you are also working in Lie algebras, but sometimes. Are there some analogies of Basser theory in the case of Lie algebras?
No. I mean, it would be interesting. I mean, it's in general, I mean, there is, like Gromov tried to do something for rings, like, for example, we're talking like when we're talking about trees, we're talking about some sort of hyperbolicity, right?
Yeah.
And, one of the interesting questions, like, okay, so we have hyperbolic groups, like we have trees. What is the generalization for rings or algebra? And I think that Ilya Rips recently put, Ilya Rips, Agata Atkarskaya, and Zhenya Plotkin, they put some paper in the archive about small constellation rings. I mean, Lie algebras, I mean, that's the same thing. So basically, it's an algebra, rings and algebras.
Yeah.
So it's, it looks like groups have much more actions, like much more.
Yeah.
Kind of, but it is like certainly you cannot generalize exactly this thing, but it's interesting, like what is the analog of hyperbolicity in a group? What is the analog in a ring? What is the analog of small constellation? What is an analog of like action on a tree or a space or a graph? So I don't think something is done about it. But that's a good question because everybody kind of is thinking, how can one do it for rings?
I can see Eduardo here, Martinez Pedrosa, and we discussed with him this topic. That's the idea is to go to homological versions of this theory. And in that case, you have to go from Lie algebra to the enveloping algebra of the Lie algebra and consider category of modules of the enveloping algebra. So if there is some analogy of Basser theory in homological language, then this could be translated into Lie algebra language.
There is like first book, has more like than I said, and I think there is some analogy. So so you mean through homology?
Yes, through homology.
Yes, that's interesting. Yeah, but it would be very interesting, like if somebody can do something like similar in the algebras.
Well, of course, we have three products in Lie algebras. We don't have good H&N extensions, but still something can be done. Yeah, but what geometrical object do they represent? I think in the case of Lie algebras, you have to move from like discrete geometry to something a little bit different.
Yeah.
Okay, I'm quite happy with this answer. Thank you.
Any other questions? So I had a question on one of the slides. There was the Boon's lemma, and there were two items in it. And I think second item is a corollary of the first. Is that right?
Let me see. Like what is it?
So the first item said that Britain's, sorry, not Britain's lemma.
Yes, it is. Yes, because then you take a normal form of this. So if it doesn't contain subwords, then the normal form is non-trivial. Yes, right. It is a corollary. But it is like, I put it here because it is kind of,
it's exactly the statement they use in the construction.
They use in the constructions of Boon and Novikov. Like they needed something to say that some word is not equal to one, like one word is not equal to one.
Right. Okay, thank you. Any other questions?
I think they call this letter T like a passing letter.
Yeah. It's I forgot. Not a passing letter, but it's something. How it's in Russian? Проходная. Okay. Then it should be passing letter. Yes. Usually,
I was at seminar where the Novikov was talking about this construction years ago in the Steklov Mathematical Institute. So I remember that was very impressive at that time, the solution of the word problem.
Yeah, it is like, passing letter, I even know why it is. Like, I can make a drawing. Like, if you have an H&N extension, how the diagrams look like? You have a diagram, like, okay, one counting diagram, like if some word is equal to 1, it can be written on the boundary of the diagram with cells. And when we have an H&N extension, we have these things like strips, like of this letter T. Or maybe no, like this, maybe. Yeah, if you have T on the boundary, then you have this letters T.
Yeah.
And this is why it is a passing letter, like it goes from here to here. And you cannot do anything about these strips. Like, this is how the diagram, like the diagram consists of things in this group H and these T strips. But now they call it stable letter, basically, like letter T in extensions.
Yes,
stable letter. Letter which this letter does not disappear because no relations, like it appears we have t inverse and we have t in the relation. So it's exponential sum of t in the relation is 0. So the letter, if it appears, it does not disappear
That's right.
from the word.
Okay, I'm done with my memories.
Any other questions?